Okay, everybody, I've given myself a little bit of a challenge here. I want to explain the three main theorems inside section 1.3, spending about 5 minutes on each of them, just to try to sort of reiterate what the book says and to possibly illustrate it in a way that might be different than just reading. Okay, so we've got 5 minutes on the clock over here somewhere. Okay. Let's go ahead and get started with what's called the mean value theorem. Okay, the idea pictorially behind the mean value theorem is that I've got some function f. Okay, here's my f of x. Okay, and that function has an average. Let's call it f av. When I consider some interval, let's say a to b, it doesn't matter where I put it. Here we go. Okay, now the formula for computing the average is that I take the area under this curve, which is described as the integral from a to b of f of x dx, and then I divide that by the length of the interval. Okay, this is a natural analogous way of computing average that we have when we have discrete values. Here we've got a nice smooth continuous value, and we're going to label this f of av. Not f of av, f av. As just, hey, this is the average value of f. Okay? Now, what the mean value theorem says is that somewhere in here, not really sure where it is, okay? Actually, I know exactly where it is. There is a value c such that f of c is the same as f sub av. Okay? So if I want to make this clear, here's f of a, and okay, here's my f of b, let's say. So neither one is exactly the average there, but this value c, this exists. Okay, now this is a rather straightforward, okay, it's an assertion, it's rather provable, but the question that a lot of you have is well, how would I use this in a setting? Well, here's what the problem would give you. It would give you f of x, a, and b. And then what we tasked to find is f of c, or better yet, the actual point c where the average occurs. Okay, so how would we do that? Well, let's say f of x equals, let's say the value x, a equals 1, and b equals 3. Okay, then I can use this formula right here, 3 minus 1, the integral from 1 to 3 of x dx. Okay, what does this graph look like real quick? It's a triangle from 1 to 3. Means I can compute the big triangle's area, which is 3 times 3 over 2, and subtract from it this little triangle's area, which is 1 times 1 over 2. And so what I get is 9 halves minus 1 half, or 8 halves, which is the same as 4. So I know this part equals 4, and this part equals 1 half, so I have 1 half times 4, or 2. Okay, this is my f av. That's my average value for the function. Okay, now, because of the mean value theorem, I know there exists a point c. There is a c where f of c is the exact same thing as f sub av. Okay, so that means I know there is a point c where so f of x equals x, so f of c is the same as c, which also needs to be the same as 2, so I know that c equals 2. Okay, if it was a little bit uglier, and I'm not going to write down what f of x is, I know what I'm looking for is the f of c, which equals f av, And as long as this function's invertible, I can say that C equals F inverse of whatever the average is. And that's how I could find the point C. Okay? And what's really interesting here is what this all means, this existence of point C, is that there is a rectangle that you could find for any function here where the area of this rectangle is the same as the area under the whole function. Pretty neat. That's about 5 minutes. Okay, great. The next theorem that we're moving on to here is the fundamental theorem of calculus part 1. All right. And the fundamental theorem of calculus part 1 has to do with the definition of a function. So let's go ahead and hit start. Boop. Starting. Okay. We're first going to assume that f of x is continuous. And the best way that we can understand continuous means I can draw it without lifting my pen off the paper. Okay? And it's basically going to be continuous over some interval, let's call it AB. Okay? We're going to define a function big F of x. Okay? We don't know what f of x is. This is how we're defining it. Big F of x, I want this to be the same as the integral from some point A to some point x of f of t dt, where x is any point inside the interval AB. Okay, so that's the definition of what big F is. Okay, whatever this would be when we end up solving it. Then, what the fundamental theorem of calculus part 1 says, it is true that big F prime of x is the same as little f of x. This is super awesome. Okay? What having a variable in the top limit of this integral means is that I'm not quite sure what this area is going to be, but I want it to be a function of wherever I choose to stop. Okay? So it's always going to include A, but maybe it'll stop here at this x. And this is an area which will be a function of whatever point I choose. Or maybe I want to choose a different x. Let me go ahead and do that in a different color. And now this is the area, or maybe a different x. Let's make this one close. And this is the area. Or I could even choose an x that is, in fact, the b. And this is the area. And so what big F is in this context, it's the area depending on where I chose to stop it. See, it's a function of x. So it can be this one if that's the value of x, or to return this number if that's the value of x, or return this number if that's the value of x. This right here is just some function. It's easy to get caught up in this f and that f, etc., etc. If you want, you can just say the area under the curve, depending on where I stop, is equivalent to, well, just write down what it means to calculate the area under the curve if I stop at the point, where is that light coming from? Stop at the point x from over there. Okay, boop, boop. I hit it. Okay, now if I define A in this way, then the derivative of A is going to be the same thing as the function I started with. This is an extremely powerful theorem, okay? It is pretty straightforwardly proven in the book here, but it involves basically relying on the limit definition of derivatives. I've got 1.5 minutes, so let's go ahead and kind of try to work our way through that, okay? Now, big F of x, the derivative of that with respect to x, just using the limit definition of derivatives, is the limit as h goes to 0 of f of x plus h minus f of x over h. Remember, this is kind of like a weird 0 over 0 thing, but Now I'm going to use the definition that we set forth for what each of these integrals are. I'm going to pull out the 1 over h. And now what is this? This is the integral from a to x plus h of f of t dt. And this is the integral from a to x f of t dt. And remember, this is just by definition. This is what I said big F was. This is what I said big F was, etc., etc. Okay? Now what I can do is something really cool. The limit as h goes to 0 of 1 over h of, I'm going to flip this. And then what I can see here is I'm going from x to a, that's this one, f of t dt. The minus sign is gone because I reversed the order, plus the limit from a to x plus h, f of t dt. Now, by the by the integral rules, I can squish those together into a single integral that looks like this, x to x plus h, f of t dt. And this is exactly the definition right here of the average value. Okay? And because this is the average value of the function over this teeny tiny integral, I know there is a c in that interval, which will be the same, yada, yada, yada. Okay? Like I just went yada, yada, yada. I ran out of time, so I'm done explaining it. But these are the basic steps. This is definition, manipulation, squishing together. And then from here, we make a recognition that this is the average value and then use the mean value theorem. Okay? More than 5 minutes. Whatever. Okay? The last one I want to do is the fundamental theorem of calculus part 2. Now, both of these things feel really, really similar, but they are in fact quite different and they are proved in different ways. Okay? So again, whoops, I got to start my time. Boop. Okay. F is continuous on AB. And f of x is any antiderivative of little f of x. What that means is that big F prime of x is the same as little f of x. Okay? Then what we've got is the integral from a to b of f of x dx is the same as big F of b minus little f of a. I'm big F of a. I don't know why I said little f of a. I apologize. Okay? This seems wild. Okay? And there's a lot of like funky ways to prove it, etc., etc. But what I want us to pay attention to here is that this is any antiderivative. Okay? Now, the reason why it says any antiderivative is if f prime of x equals little f of x, then the derivative with respect to x of big F of x plus any constant is also going to be equal to little f of x. So how many antiderivatives do we have? We have an infinite number of them. Okay? And what's nice here is now I can evaluate the area under a curve from A to B simply by knowing about an antiderivative. Okay? I've got a lot of extra time here, so let's go over an example of how to use this. Okay? So let's say I want to find the area from, again, let's go from like 1 to 4 of, so I need an well, let's just go ahead and write x squared dx. I want to know what this answer is, and I want to use the fundamental theorem of calculus part 2 to solve this. Okay, so what am I looking for? I need a function big F of x such that the derivative of big F of x is the same as x squared. Okay, this is the sort of backwards game we're playing here. We're going to construct rules and the whatnot, but for now, let's play this game. Okay, so when I take the derivative, it's going to equal x squared. Well, let's go ahead and start with a guess of x cubed. Why would I guess that? Well, because the derivative of x cubed is 3x squared. And we notice, I've got an x squared. I've got an x squared. But oh crap, there's an extra 3. How would I get rid of that 3 is by dividing by it. So let's make a new guess. Let's say 1/3 times x cubed. So now when I take the derivative of this, I got 1/3 times 3x squared, which equals x squared. So this thing right here, my guess, 1/3 x cubed, is an antiderivative of x squared. In other words, its derivative is x squared. So let's use that fact. I'm going to take this function and evaluate it at the upper endpoint. 1/3 times 4 cubed. And then I'm going to subtract from that, evaluating this at the lower endpoint. 1/3, 1 cubed. What's 4 cubed? 4 times 4 is 16, times 4 is 64. So I have 64 thirds minus 1 third equals 63 thirds. And that will be my answer. Pretty neat, huh? I still have a whole bunch of time left over. I think it's important to look at the proof of the fundamental theorem of calculus part 2, but it is in fact the hardest proof out of between the mean value theorem, the fundamental theorem of calculus part 1 is pretty straightforward. This one right here is the hardest to prove. I'm not going to expect you to prove it on any exams or in homework and stuff, but it is critical to kind of understand where it comes from. You make a partition and you start considering this guy right here, f of b minus f of a, along that partition as a summation. And then doing some manipulations from there, you arrive that that is going to be the same thing as the Riemann sum for this bad boy, basically using the fundamental theorem of calculus part 1. Okay, a long video. I'm done. Have a good day. Bye-bye.